So here's the last two problems of class today on Tuesday, January 21st for momentum conservation of collisions. And these ones are a little bit more involved, and I want to walk you through our work for these. We did these in class. This is a classic problem, a bullet being fired and being embedded into something else. So here's our setup. We've got a 10-gram bullet fired at a 1 kilogram block, and it lodges itself into the block. And the two objects, the bullet and the block, move together after the collision. And after they move, they slide for 4 meters across the floor, and we have a coefficient of kinetic friction for the block on the floor, and we want to know what's the bullet's initial speed. So let's call this initial speed VB, for B being for the bullet. And you want to break this problem down into two individual sections. Section 1 is the before and after the collision, and this after would be immediately after the collision while the block and bullet still have a velocity. Let's call that velocity final, the final velocity after the collision. The block bullet system would then slide across the table, losing energy to the surroundings in the form of heat due to the friction, and that would be our second section of our travel, the block losing energy to the surroundings. So right now, let's just consider the collision. Immediately after the collision, we're going to assume that this block and bullet system have not lost any energy to the surroundings yet. We're going to have it be two independent events. And that means that I can have my system initial, momentum initial for my system, equal my momentum final for the system. You can only do this if you don't have an external force. So we can't consider this whole problem in one step. We have to do it in two steps. One step momentum, one step our friction force, okay? So my momentum initially for my system, the only moving object is the bullet. This is stationary, so it has no momentum. So the momentum of the system is the bullet. Convert from grams to kilograms, multiplied by its velocity. We don't know it. We'll call it VB. The momentum for the system at the end, these are combined objects. Since they move together with the same velocity, we can treat this as one big object with the mass 1 kilogram plus the mass of the bullet. That's how I get 1.010 kilograms times its velocity, V final. And we don't know V final either. So there's two we don't know. Well, we can figure out V final if we consider what happens with friction. So we know that this final velocity, you can think about it, the initial energy here, kinetic energy, gets used up to travel 4 meters. And then I have an initial final velocity of 0. So I can say that change in kinetic energy is equal to my work due to the friction. Well, the kinetic energy is kinetic final minus kinetic initial. The initial kinetic energy is what we're solving for. The final is going to be 0. There's no velocity at the end. And the work of friction is just the force of friction times its displacement. Well, the force of friction would be our coefficient of friction times m times g times my displacement of 4, and the force is in the opposite direction as the displacement. My force of friction would be this way. Therefore, we have a negative work. Our negative sign on this side will cancel, and we'll be able to solve this equation for our final velocity, considering our kinetic energy being 1/2 m, the combined mass of the block and the bullet, v squared. And if you solve for your final velocity, you get 3.9598 meters per second. That final velocity can be plugged back into our momentum initial, momentum final. We don't know VB, but now we know VF. Plug that in, and we can solve for VB being 399 meters per second, which is about 400 meters per second for the bullet. You can do a second approach to that if you'd like, a Newton's second law approach. Newton's second law is our acceleration is equal to our force, our net force divided by our mass. And we can treat this system as the net force of friction divided by the mass, and I get an acceleration, 1.96. This should be a negative 1.96 meters per second squared. Then I can use kinematics. Plug that in here. Our final velocity is 0. Our initial velocity is what we're solving for here at the start. 2 times our negative acceleration times our displacement. And we get the exact same value. This can be plugged back into our momentum, and we get the same answer. If you follow the math through this, it's the same math required to solve this equation here. You do the same math, just two different equations or different approaches to get to those answers. So that's how you solve that one. Now, the last one we looked at is called a ballistic pendulum. And a ballistic pendulum is a bullet being embedded into a block that doesn't slide, instead it swings. So this bullet gets embedded into this block of mass m. It swings up to a height h. That's the maximum height it reaches, so it's stationary there, and then it swings back down. They want to know what's this initial velocity of the bullet in terms of all the other variables. So no numbers here, just variables. How do you approach this problem? You consider this height here as a change in gravitational energy, and the gravitational energy we have here has to be equal to the kinetic energy we had here of the combined bullet block system. That's our first step, breaking it into an energy, and that'll allow us to solve for the final velocity of the block and the bullet just after impact. So here's my m times g times h, my gravitational energy, equals my kinetic energy, 1/2 mv squared. That would give me my final velocity in terms of g and h, equals the square root of 2 times gh. The momentum approach would be just before a collision of our bullet and just after a collision of our bullet. Those momentums have to be equal. There's no external forces. So the momentum of the system initially is just the mass of the bullet times its velocity. That equals the momentum of the system final, the combined mass of the bullet and block, times its velocity at the end. Well, we know the velocity at the end related to my height is equal to square root of 2gh. I can substitute that in and solve for my final velocity of, my initial velocity of my bullet. This would be VB, we can call it, the velocity of the bullet, and it equals this. So if you tell me the height and I know my masses, I can tell you that initial velocity of the bullet.